All right. Well, I think we're ready to start. So, happy week before the week before spring break. um, things are drawing rapidly to the middle, which is good. Um, I was just thinking, as I was going through things, it's not about a year ago. We were getting ready to go on spring break, and then of course, campus closed down, and for this class, um, we kind of just switched to just projects, and stopped meeting because no one knew what was going on, and it was the asynchronous world was the better world. And so I'm really looking forward to this spring because I know that's not going to happen. And I think with the practice we've had now, uh, like I didn't realize until I started doing the synchronous Zoom classes in the fall, and I think even with this class, how much I sort of miss seeing people's faces, even if it's on Zoom. I mean, it's better to be in person, but I get my grid up. I can see all you guys at once. I'm in my virtual classroom. My cat might come and meow at me, but I can sit and drink my cup of coffee and visit with you guys. So that's okay. Things are getting better. So speaking of which, sort of housekeeping things. So next week, you guys all have your first sort of group reports. And I don't necessarily expect that you've gotten a ton of really detailed work done by next week. It's just sort of a first chance for you guys as a group to do a little short presentation on your project and start to pull your thoughts and ideas together. So I'm going to try to give you some time on Tuesday next week to make sure you're organized a bit in class. But I do, obviously with the group project, you need to be meeting outside of class as well, or you don't necessarily have to meet in person, right? You can do asynchronous things too. There's certainly sometimes I find when I'm with a group, if we're trying to get something done, sharing a file, sending emails, as long as you're sort of organized and you're not rewriting things that other people are doing, that can be a pretty efficient way for a group to bring something together as well, especially if timing doesn't work well for everybody. But that's coming up right before spring break next week. Originally, the syllabus I'd sort of planned to rush through the first half of the class and get to more the human side. But again, I didn't realize how good the Camden conference was going to be. So we've already kind of we have a jump start on what I was going to do the second half of the semester anyway. So I think I'm not going to go quite that fast because I'm looking through my slides of sea ice thinking, how can I show you one or two? And I'm like, well, I can't really show you one or two because it's so interesting. And especially for group projects this year, since you guys all are focused on sea routes, I mean, understanding sea ice and some of the terms and stuff like that, I think is actually quite useful. So we're going to spend most of the day focused on sea ice. Hopefully we'll get through it. I think we will. Or part one of sea ice, because as we learned last time, sea ice has two components, right? Or if we talk about ice on the sea, there's two different components. Does anyone remember what they are? Someone tell me one of them.
Sea ice.
And what do you mean by that?
Ice that's on the sea.
And where does that ice form?
Oh, hold on. I guess right off the coast, right?
Pardon?
It breaks off from those glacial areas, right?
Okay, no. That is one type of ice on the sea. But when we talk specifically about sea ice, where does sea ice form?
On the sea?
In the from frozen ocean water.
Yeah, so sea ice, when we talk about sea ice proper, it's actually frozen seawater. So it's actually forming on the surface of the ocean. Patrick, what the stuff you just talked about, that is ice on the sea, but what name do we give to that ice on the sea? Anybody? Dylan.
Well, that's like a calving glacier, so wouldn't that be an iceberg?
Icebergs, yeah. And so it's really you know, a lot of people think of sea ice and it's just like, oh, it's just any ice on the sea. But what's important is because the process of actually forming ice by freezing the sea surface versus pushing ice that's formed on land into the sea, it gives you two different types of material in the water that behave very differently. Sometimes they don't look that different, but actually the processes are quite important because sea ice, it turns out, I'm not going to tell you how thick, but it doesn't end up being all that thick. Because once you grow a thick enough layer of ice, you kind of insulate the water below from the air surface, and so the ice growth really slows. On land, you guys, let's see, you guys did you finished the Greenland thing, right? How thick is the Greenland ice sheet when you did your cross section? Just some general numbers. Any ideas? Barbara, how thick did you find ice?
3,400 meters.
3,400 meters. That's pretty thick. Now, we're unlikely to have an iceberg that's that thick, but when you have ice that thick that's being pushed out to the coast, you can get glaciers that are calving, like Patrick was talking about, into the ocean, where you have chunks of ice that are 150, 200 meters thick. And you just can't do that with sea ice, at least not in sort of present climate conditions and probably climate conditions on Earth in general for the last several million years. So that gives those two types of ice very different properties. And they're both important when we're thinking of shipping and moving across the water, because you can deal with them differently. You can have an icebreaker that can go through relatively thick sea ice. Any battle between an icebreaker and an iceberg that's any size, the ship's always going to lose, because the iceberg is going to be, you know, if it's 50 meters high, it might be 400 meters deep, and so it's just so thick that no modern ship, you could shoot it with a missile or something, I don't know, but there's no way a ship could go through it. And so they're very different things to think about. And we'll talk about those. Thursday, we're going to do a deep dive into icebergs. I got a couple of videos that I think are pretty fun to watch. And they give you a good sense of what the process, like that Patrick was talking about a few minutes ago, when the ice breaks apart. Okay. So mainly this week, we're going to do things in class. You guys have your background projects to be working on. We will have a quiz Thursday. I put the rivers up. We're just going to add rivers. There's only like 6 rivers. So I apologize for not putting them up last week for you to look at, but it's only 6 new things, and they're pretty spread out. There's only 2 big, these are just the major rivers, right? I mean, there's thousands of little creeks, streams, whatever, but really the major rivers that bring large volumes of fresh water to the Arctic basin are only 6. And only, you know, there's only 1 in Canada. There's only 1 in Alaska, and that one actually doesn't run directly into the Arctic basin, but it does run into an area that's close, so it can get into the Arctic basin. And the other 4 are all in Russia. And partly that tells you, again, that emphasizes how big Russia is. But and the rivers in Russia actually drain pretty vast quantities, because some of the mountains that they're draining are actually quite a ways south of the Arctic. But they drain to the north into the Arctic basin. So look those up. So obviously, if we only have 6 new things for the quiz this week, but we have sort of our typical 20 question quiz, something like that, 25 question, there's going to be a lot of review questions. So make sure you're going back, you know, your countries, you know, your cities, you know, your other features that we've been studying. And as we're adding smaller bits to the geography, you've got more stuff to know, but a lot of it's review. And hopefully it's kind of solidifying your physical geography of the Arctic in your minds. Okay. Yeah. So next week will be a bigger week in that I will 3 topics we're going to cover: sea ice today, icebergs on Thursday, and then permafrost. And I won't take all the time Tuesday for permafrost, so you have some group time. If we don't get through permafrost, we may do a little bit of that when we come back after spring break. And then, but pretty quickly after spring break, then we'll do more of a deep dive into ecology. But like I said, iceberg, sea ice, even permafrost will be all things that you guys are going to encounter as you start looking at your specific areas, either on land or in the sea. So I think it's worth spending a little bit of extra time on those. Okay, does anyone have any questions for Tuesday morning? Okay, so the first thing I want to do is, where are we? Here we are. Yeah, so we're going to take the first part of the ice on the sea apart, and we'll focus on sea ice today, talk about what sea ice is, how it forms, what's happening to sea ice today, and then really importantly, how do we monitor sea ice yearly? It's kind of neat with sea ice in particular, because there is a global community that puts all kinds of information online for free. And this is because of the importance of sea ice to a lot of different types of people who travel on the oceans, whether you're shipping stuff or you're part of a fishing fleet, for example, or you're part of the military driving around doing exercises. And so basically almost every Arctic country has their own sea ice service, which puts maps and satellite images online free of access, tracking sea ice on a weekly basis. And so we'll get to that. And some of that is going to be really important for you guys as you're starting to look in more detail at your sea ice routes. So actually on Moodle for topic 5, you'll see there's a bunch of links that are, Canadian Sea Ice Service, Russian Sea Ice Service, etc. And those are links to websites that you'll want to go and explore depending on what your route is, because the countries all work from kind of the same satellite data. So the maps should be relatively similar, but some of them may be more detailed for specific countries if it's, ice like close to shore and whatever. Okay, so the first thing I think we need to do is take a few minutes and think about what sea ice is. Is it all pretty much the same? And when I say sea ice now, we're excluding icebergs. This is sea ice proper. So is it all pretty much the same? What does it look like? And so we're going to do about a 5-minute sea ice blitz. And so I'm going to just randomly put you into breakout rooms. Yes, breakout rooms. Stop share. Interesting. Oh, there we go. I'm going to randomly put you into breakout rooms. And what I want you guys to do in your group really quickly is I'll put you in 5 breakout rooms. I want you to go online and find and just Google sea ice. And you'll be in your breakout rooms, but everyone can do a quick Google search on sea ice in your breakout room. And then I want you to come together and really quickly share your thoughts and see if you can develop a really quick mental image of sea ice that is somewhat more detailed than what you have right now at the start of class. Okay. So I'm going to go ahead and put you in breakout rooms. I will call you back in 5, maybe 7 minutes, because I guess if you're all online, it may take a minute or two. But right, this is the power of Google. We could get an answer to a question almost as fast as electrons can zoom through copper into our computers, or through the air if you got Wi-Fi. Okay, so everyone know what you're doing? Okay, so you're going to go into breakout rooms. Go ahead and go into whatever room, say hi to people, and then jump on Google. And I'll give you like a 2-minute warning through messages. All right. So is sea ice just exactly what you expected it to be like? Pretty much? Sammy's saying no. We'll get you just a second, Sam, once everyone gets back. We almost there? We should be almost there. Anyone else in the breakout room? Okay, so Sammy, I ask a question as people come back on. Is sea ice what you expected it to be? And Sammy was shaking his head. Well, why are you shaking your head, Sammy? What did you see? What's one thing that you observed that your group talked about that wasn't what you were expecting?
There were a couple of things. I was on the National Snow and Ice Data Center website,
Uh-huh.
and they at one point they were talking about how the sea ice actually reflects up to 80% of the sunlight, and how that can actually help cool the Arctic. But when the sea ice melts, the dark water beneath it ends up absorbing all of that light, and it has the opposite effect. And then Maddie actually found some information about how sea ice doesn't play a role in sea level rise, because it offsets, like sea ice is already displacing the amount of water in the actual sea ice. So when it melts, I guess it has a very little effect on the overall sea level. So
yes, so excellent. So that first thing you read about and you hear sometimes something called Arctic amplification. And one of the observations that's quite striking with climate change is that the Arctic is warming much faster than the equator, for example. Even though on average, basically, most spots on Earth get about the same amount of sunlight over the course of a year, actually. It's just in the Arctic, it's really concentrated. But this idea of Arctic amplification is exactly partly what Sammy mentioned there. So when you've got sea ice covering the oceans, insulates the ocean temperatures, but also reflects a lot of sunlight. So ice has a high albedo. Remember that, my favorite song. But as you start to melt sea ice a little bit and you expose water, water has a low albedo, and water actually absorbs solar radiation. And so as soon as you start to get a little bit of open water, if there's the sunlight the next day then is absorbed by that water, and then at night the water cools off and gives the heat back, and that continues to melt the ice. And that then raises atmospheric temperatures, because then you're not reflecting a lot of that solar radiation as energy. It's staying in the system. So that's one of the reasons why the Arctic is actually warming 2 to 4 times faster than the rest of the planet. It's one of the reasons why we see the impact of global warming faster in the Arctic. So really important. And then the old sea ice trick. It's also, it's definitely one of the misconceptions sometimes we have. It's like, oh no, the Earth's going to flood because the sea ice is all melting. Well, we have to worry about the glaciers melting, but not so much the sea ice. And if you wonder how this works, take a glass of water, put an ice cube in it, fill it up to the very brim. So like you're about ready to overflow the glass, but you'll have an ice cube floating on top, right? And the ice may actually be sticking above the level of the glass, and sit there and watch it melt. Okay, so don't, unless you have nothing to do, don't actually sit there and watch it melt, but you can come back and check, right? And what you'll find is the water never spills out of the glass, because the ice is already displacing, as Sammy said, the volume of water that the ice is going to turn into. And that's because ice has a density that's about 0.9, or only 90% of the density of liquid water. And so once you have sea ice that's actually floating on the water, if all that sea ice melts, you actually produce less liquid water by volume than you had sea ice by volume.
Yeah.
So when we worry about a sea level rise, which is a huge realistic problem, we're not worried about the sea ice melting. There's other problems with the sea ice melting, but we're really worried about land ice, or ice that's actually not being supported by floating on the water, but ice that's stuck to the land. When that melts, then that water actually does add to sea level rise. So those are both great points. Jackie G, anything your group? What did you just see personally? Like were you surprised? Is this what you expected when you guys started looking at sea ice?
We were surprised by the same things as Sammy's group, but we also found out that the cycles of sea ice contributes to the ocean's currents and has a big impact on that as well, which is interesting.
Yeah. So one of the big things that drives ocean currents is wind. And not all waves are driven by wind, but a lot of them are. So if you have an ocean that's totally covered by ice, you don't get a lot of waves. You can still get waves that actually go under the ice from the edges. But as you start to melt the ice, you have more open water, and that allows waves to be produced. And then those waves can go and rock the sea ice and can actually help break sea ice up. So there's a really interesting dynamic between wind and waves and sea ice. So that's quite important as well. And then also ocean currents on sort of a broader scale as far as moving sea ice around. That's good. Let's see, Catherine, anything you found unusual or shocking?
We talked about how the salinity of the sea ice changes over time. So when they first freeze, the ocean is very salty, and so the ice is a very low freezing point. But over time, the salt gets kind of trapped in these pockets, and over time they kind of become more freshwater, so that it's easier for them to stay frozen.
Yeah, as the ice starts to form, you get the ice is pretty pure, so not much salt in the ice, and the ice crystals themselves, if they get little pockets of seawater brine in them, they'll actually force the brine to diffuse out through the ice. And we actually saw this in 2016, one of our Arctic trips. We actually we lived on sea ice for about a week. It was an amazing experience. So you'd hear it creaking and all this other stuff. But we, a couple of times we went out with an auger and we drilled down through the sea ice to see how deep the sea ice was. And we drill a little bit, and then we had a salinity meter with us. And so, because you drill into the ice, and this is like early June, so the ice is starting to melt. So as soon as you drill to the surface, you hit little pockets of water. But you can see progressively as we drill deeper and deeper, the pockets of water we hit got more saline. But then when we got to the bottom and it flooded with seawater, like the salinity jumped from 900, maybe 1,000 parts per thousand to like 10, 20,000 parts per thousand. And so you could really see how the seawater itself was a lot more briny, had a lot more salt in it than the water that was contained kind of in layers and pockets within the sea ice. So that's pretty cool. Let's see, Rob, is there anything that you found surprising as you guys were looking at sea ice and talking about sea ice?
Not really. I was looking at the National Snow and Ice Data Center, so I didn't really find anything new that the rest of my group didn't see already.
Okay. Did anyone look at pictures of sea ice? Anyone see any pictures of sea ice? Patrick?
I was looking at the different cycles and how it forms in terms of like sheets versus what they call like nylas versus these like how they pile up into rafts in a more smooth water versus choppy water, and their different formation styles, and then also in relation to smooth, like fast and slow ice.
So lots of words, and I've got some diagrams to help explain some of those words, because you just said about 20 vocabulary words in 3 sentences, which is great. And we're not going to become experts, but part of that is part of covering a bunch of things. There is a whole, for all of these topics we cover, just like with glaciers, there's a whole vocabulary, like textbooks written just on sea ice. And we're not going to go into that depth of detail, but fortunately, places like Patrick, what you're talking about, the U.S. National Sea Ice Center has a lot of information. There's actually something called the Ice Man, which is an sea ice manual that you can find online that talks about a lot of the technical ways we describe sea ice. So anyone that really is interested in that, there's a lot of information online about more of the technical details, although we're going to talk about more of that in just a second. Anyone else, last minute, some amazing thing you saw or something that changed your way of thinking about sea ice that you desperately want to share with us? Okay, so what I will do is I'm going to share some sea ice with you. I have really been privileged, I have to say, in my career at Dickinson, to be able to spend time with sea ice and icebergs, and it's truly amazing stuff. So these first few pictures are going to be. Can I get this to work? Yeah, come on. Yeah, so these first set of pictures. These are all pictures I've taken either out of a plane flying into the Arctic or on the ground. And so this is some pretty typical sea ice. This is from the trip where we actually camped on sea ice. This is in Baffin Bay. So you guys all know where that is. And so this is sea ice starting to break up. But to me, this is pretty typical of what I would have thought of before I started going to the Arctic, that this is what sea ice looks like. It's just a bunch of white, big, slabs of icy stuff floating on the water. They have some different shapes. And actually there is a little thing right there that's not sea ice, even though it's ice in the sea. What's that? Can you guys see what that little thing is there I'm circling? Barb?
Looks like an iceberg.
Oh yeah, Jake, yeah, that's an iceberg. So this is in a particular spot where there's not a ton of icebergs compared to the amount of sea ice. But there is some icebergs there. Actually, there's another little iceberg probably right there. You can see here there are two ice floes that have either been broken apart or maybe they've been glued together. You can see the seam going down the middle. But for the most part, there's not a lot of texture to this sea ice. But there is sea ice that does have texture. So this is sea ice that's later in the summer, and this is further north. This isn't Baffin Bay, but this is further north and more into the Canadian archipelago. This is between Resolute Bay on Cornwallis Island and Ellesmere Island. And so you can see this is also sea ice, but it's got lots of different textures. And part of the reason I would show you these maps is because as we, towards the end of the talk, and as you guys are looking at your, the sea ice charts for your particular routes, what you'll see is we classify sea ice by extent of cover, by age of the sea ice, by estimated thickness of the sea ice, and then sometimes also by some different textural characteristics. So even though both these pictures we've seen, neither one of them is 100% ice. Now, if we were flying over these areas in, like right now, probably in March, they might be almost 100% ice cover. But even in the North Pole in the middle of winter, because of the things that I think Jackie was telling us about, wind currents and ocean currents, the ice is always kind of in a state of stress. It's almost kind of like the tectonic plates on Earth, actually, kind of analogous, because there's stuff moving underneath it. Even though the ice itself is relatively rigid, it can break apart, it can run into other bits. And that's also similar to what we see with tectonic plates, just at a much, much slower scale. But you can see here, there's sea ice that's still kind of white. But what's one of the things you notice about this picture right away that's different from the picture we just looked at? If you look at the surface of the ice. I'm not sure if I can go backwards easily. Can I? Oh yeah, there we go. So this is this sea ice compared to this sea ice. What's an immediate difference? Matt, do you see anything different between these two?
This sea ice is a lot more broken up, it seems, and the ice towards the right has like puddles of water on top.
Yeah. So this is a fascinating thing. I'll show you a picture at the end. It's a little disconcerting, but sea ice, of course, can still float if it's got some water on top of it. And you know, this is one of the reasons that how you know that this is going into spring and summer as opposed to going into the fall, because the sea ice melts from the top as air temperatures warm, and it can develop all kinds of little lakes and even streams. And here you have interconnected water that can actually flow across the top of the ice. And so when sea ice melts, a lot of the melting is actually from the top down, because the water underneath isn't really changing temperature very much during the course of a year. It might a little bit, but actually not that much. What's really changing is the amount of radiation and the air temperature above. So a lot of sea ice actually melts from the top down during the course of the summer. This is another picture that, I mean, I just love these pictures. I can look at these forever. There's so much detail and texture in this that just isn't what you'd expect. Like, you know, the 2 slides ago where everything is just a big mass of white blocks. There's all kinds of detail here. And a lot of this detail also has to do with how old the sea ice is. And this is also really important when we think about the formation of sea ice, because sea ice can only grow about 1 to 2 meters a year. If you just do the basic thermodynamic calculations of heat loss and crystallization rates, sea ice can only grow, you know, 1 to 2 meters a year. That's about the extent that it can grow in the Arctic. But there are times when you get sea ice that can be 5, 6, 7, 8 meters thick, even 20 or 30 meters thick. But the only way that can happen is if some of that ice doesn't melt during the course of a given year. So if you have, you know, 1 meter's worth of growth 1 year, and then the next year that ice hasn't melted, it can grow another 2 or 3 meters. And so that's one way that ice can actually get thicker. But the other thing that can happen is ice flows run into each other. And when that happens, you can get ice that pushes up on top of another ice, and you can start to artificially increase the thickness of the ice as well. But to me, when I look at this picture, you can really pick out the pieces of sea ice, and you can see they're all different sizes, which again is really important. You know, an icebreaker might be able to go through some of this area where there's relatively small bits of ice. It may even just be pushing the ice apart. Would be tougher to go right through the middle of this big solid chunk of sea ice. And to some degree, you can tell, not totally, but you can tell somewhat based on color. Generally, the whiter sea ice has got fresher snow cover, and a lot of times that means it's younger ice. And so you'll see we classify sea ice based on first year, second year, or multi-year sea ice. And again, with shipping, that's really important because multi-year sea ice is harder to get through than first year sea ice. On the other end, multi-year sea ice means it can survive during the summer. So from an animal perspective, if you're a seal or a walrus that wants to haul out on land to rest for a bit, or if you're a polar bear that's hunting on sea ice as a platform, that multi-year sea ice is really important because it's not going to totally go away in the course of the summer. This is another pretty fascinating texture to me, and this is sort of an interaction texture between the 2 different types of sea ice. So this is what we call land fast ice, out to probably kind of the edge here where you see these hummocks. So sea ice, once it attaches to the land, it gets thick enough, it actually gets grounded on the shoreline a little bit, and then it becomes more stable. Then it can't float away because it's actually frozen to the base, like along the beach and a little bit offshore. And that's called land fast ice. So that's some of the last ice in the summer that's going to melt because it's not breaking up and drifting away in the currents. But these hummocks, these bigger hummocks, these are actually grounded icebergs. And so they're thicker areas of ice. And because they, you know, we only have about 10% of the iceberg above water and about 90% below water, these icebergs come close to shore and then they hit the bottom and they get stuck. Eventually during the summer, they can get moved off by currents, but once they get kind of surrounded by the land fast ice, now they're stuck. But the icebergs, because they go down to the bottom, they actually bob up and down as the tides change. and the sea ice also is bobbing up and down as tides change, but they don't bob at the same rate because the icebergs are grounded. And so the sea ice kind of goes up and down next to the iceberg, and that breaks up and makes these trenches around the edge of the iceberg. And so, I mean, this helps to, this is going to, these icebergs, because they're kind of points of weakness, that's going to allow this landfast ice to break up faster. But the sea ice, this landfast ice is also really important because it's some of the last habitat during the summer that polar bears can use as a platform that seals and walruses can haul out on. And you know, from a hunting perspective and a hiding perspective, it's also pretty important because there's lots of nooks and crannies. So on one hand, lots of places a seal could kind of come out and hide or give birth and be hidden from sight. On the other hand, for a polar bear, there's lots of places for a polar bear to hide behind, to sneak up if it's going to try to ambush something that's out on the ice. So to me, one of the fascinating things about sea ice is just it's not just this vast white plain. It's got lots of texture and lots of complexity, even though compared to other rocks made of minerals, you know, this is a rock that's just made of one mineral. So it's pretty simple. But the physics of it being a solid, and because it forms in these two different ways, by crystallization from ocean water and by forming on land, gives it lots of textural complexity that, you know, it's just interesting to look at visually. And then it's also a little bit kind of artistic. This is actually sea ice up in the eastern part of Ellesmere Island. So it's about almost 80 degrees north. And this is one of the field stations that we've worked at. And so when the tide goes out, the sea ice is kind of trapped in a bay. So when the tide goes out, these blocks of sea ice just get stranded, and you can go and walk around them. We'll see some crystals in a minute. They make sort of pretty reflections, and this sort of testifies to the strength of the sea ice. Like, this is just perched on, you know, these rocks, and probably 70% of the bottom of this sea ice chunk is not supported by anything. But what's holding it up is simply the crystal fabric inside the rock ice is actually giving this a lot of strength, right? So it doesn't just fall apart and collapse. And just to emphasize, right now, we're not talking about this stuff. Even though some of this is relatively flat, you can see this, there's no scale in here, sorry. This is off the east coast of Greenland, but these are all icebergs. So these are 5, 10, this big one might be 20 or 25 meters sticking out of the water, which means, you know, it's 100 meters down beneath the water. So this is different. We'll talk more about these on Thursday. Okay. So we all now maybe have a slightly better visual picture of what sea ice is. And of course, sea ice is an important part of the cryosphere in that it's very dynamic. So what you can see on this map, this is the summer extent of sea ice shown graphically. The average winter extent is this yellow line. So sea ice really changes in extent pretty dynamically during the course of every year. And so it's an important part of the dynamics of understanding the Arctic as a space. And if we look at a graph of the daily Arctic sea ice extent over the course of a year, you can see that in the winter, you know, when we got almost 16 million square kilometers of sea ice, that covers most of the Arctic basin. And even, you know, before global warming started to accelerate a lot, you know, the sea ice extent would change by probably half just during the course of a normal year. And, you know, that's just because of the 24 hours of sunlight and the extended heating in the summer. What's happening now, though, as global warming continues, because the atmospheric temperature is not getting as cold in the winter, it's getting a lot warmer in the summer. You can see that the sea ice extent is not as great in the winter, and it's becoming much, much less in the summer. So it changed by slightly more than a factor of 2 between 1981 and 2010 on a yearly basis. Now it's changing almost by a factor of 4. And so the sea ice is becoming much more dynamic. And of course, that's one of the reasons why it may be possible for more access to happen in the Arctic Basin as global warming continues. We're going to see that swing get greater and greater, although eventually what's going to happen is this is going to start to crater. And so we're going to start to, there's always going to be some sea ice in the Arctic Basin. 6 months of no light, it's going to be cold. But the sea ice extent is going to become less and less in the winter. The ice is getting thinner, and that means it's going to disappear much faster in the summer. So the record sea ice minimum still was from 2012, actually. Although 2020 came really close. And actually, this graph is a little out of date because in 2020, even though in the middle of the low sea ice, there wasn't a record minimum, in 2020, the ice didn't start to build until November. So for late October, early November, last year was actually a record minimum for those months. Okay, so let's get down to the nitty gritty for a little bit. That's big scale. Let's go small scale. This is my only chance to actually watch ice crystals form on the sea ice. And this is from a trip we took in 2016 where we were camped on the sea ice. And even though it didn't get dark at night, the sun basically went behind some mountains to the north. And so we were in the shade for sort of nighttime. It was still bright enough to go outside and read, but definitely was colder because we were in the shade. And so during the day, the sea ice would melt and there'd be little melt ponds like what you see kind of down here. But then at night, you could walk around and watch the ice crystallize again. So it's really fascinating. You can see the diagram in the lower, the picture in the lower right, all these little feathery shapes, that's newly formed ice crystals that are actually growing as I'm sitting there taking the picture. And even in more detail with my little Tabasco sauce here for scale, I thought, hot and cold was kind of, yeah, right. I'm not a professional. But you can see this little mound of ice crystals, and these little ridges are the leading edge of the crystals as this crystal is actually expanding and growing at the expense of the water. So it's really fascinating. If you can do it safely, being able to watch ice crystallize, you don't want to go out in a pond with thin ice or whatever, but it's an amazing thing to be able to watch because you can really see, these are the individual crystals of ice that are growing. That are forming that strong sea ice pad that we saw that could be supported by just a few points of contact. This is another. This is actually from the same place where those sea ice pictures were, and this is all one crystal that's reflecting light, all at the same orientation. And so this is a block of stranded sea ice. You can see, my lens cap is probably 4 or 5, maybe 8 centimeters in diameter, so maybe 3 or 4 inches. And that's about the size of this one interconnected ice crystal. So this is the foundation of sea ice, are these crystals that are interlocking, and that's what gives the big blocks strength. And you can kind of get a sense of the crystalline form. Again, this is walking around these blocks of stranded sea ice. You can see that the surface of this sea ice is still not quite snow, but almost. So it actually has snow has a higher albedo. So as long as the sea ice has a little bit of snow cover on it, that kind of protects the surface. But the ice that's below water melts somewhat faster. And then the ice that sticks up above the water during the day here, this is in early August. So the air temperature here, even though we're 80 degrees north, the air temperature some days was 70 degrees. So that really melts the ice that's not still in the water, which the water I can attest because we did a polar plunge. The water was not 70 degrees. It was slightly colder, but when you're at 70 degrees, 80 degrees, the thing to do is to go for a little swim on a sunny day just to say you did it. Okay, so one kind of detailed process chart. We don't have to go to this in gory detail. We're not going to memorize this, but it just kind of shows a little bit more of the process. So you start off with something called fragile ice, and you can take these 2 paths on your way to getting sheet ice. And these aren't mutually exclusive totally, but the idea is that when you have rough oceans, so you've got currents, you don't form a continuous surface of ice. You start to freeze, but then those little bits get broken up, and you can form something called pancake ice, which you'll see in a minute, which is really cool. You can actually see that on ponds sometimes too. On the other end, if you've got a relatively smooth ocean, you form what's called congelation ice. And so with the rough ocean, you have the pancake ice cycle, pancake ice, then you get rafts and ridges. They slowly come together and get cemented together to form sheet ice. On the other end, if you have a calm ocean, you go from frazzle ice to grease ice to nilas, which I think Patrick mentioned, to ice rafts, to congelation ice, and then eventually, if it freezes enough, you get ice sheets. So both paths can lead you to the same, totally frozen over ice, but it will produce different textures as that ice starts to melt that you can see sometimes during the summer when it starts to melt. And then this lower diagram, again, this is really simple, but just shows how you start to form new ice that's pretty fresh on the surface of the water. You can get some brine trapped inside that ice as the ice crystals grow. We see that in crystals growing from a magma sometimes. You can actually get little bits of magma trapped in a crystal that's growing in a lava flow. So that process is pretty common. And then as you get, as winter comes along and you get snow, some of the snow can actually start to become part of the ice. It also allows some gases to come out of the ice. You can trap CO2, for example, in the ice crystals as well. But the ice also is growing down into the brine. And as that happens, you're actually expelling brine water. So in some places, the sea water is becoming a little bit more salty. You get brine that's even higher than sort of a 5% brine that is showing here. And then finally in the spring, as we saw in those pictures, you start to melt the snow, and that actually starts to give you fresh water here that then starts to melt through the ice. And detailed ice crystallization processes, these two pathways are less about differences in crystallization and more about differences in external factors like Jackie was talking about, where wind can break things up or not. Okay, any questions? Again, we don't have to memorize this in gory detail, but it gives you a little idea of some of the different pathways that sea ice can take. We good? Okay. So how do we get these pathways? So we do have, large, on the small scale, like wind can vary between one valley and the next, one fjord and the next. And so, that's part of the ice forming process, but part of it also are these larger scale ice currents, water currents. So the big flux of warmer water comes into the Arctic past Greenland. So the North Atlantic current brings warm water in, but you can see there are all kinds of details of smaller little gyres or circulation patterns. And so those are going to produce different specific textures in different places. There's some large scale circulation patterns, the Beaufort Gyre. We've got transpolar drift that tends to bring ice from the Siberian coast, mainly down into the North Atlantic. This route, you can get some sea ice that comes in here. This is the nearest strait though, and it's actually pretty narrow. So there's not going to be a lot of ice transported here. We also get some of the ice that's forming, as we mentioned, down into the Canadian archipelago, which is one of the reasons why this is quite important for wildlife in particular, because this will be one of the last places where we probably have sea ice late into the summer. And that will be really important habitat for polar bears, seals, walruses, etc., even whales, smaller whales hiding from some of the bigger whales that are coming in. And then this is then again starting to show diagrammatically, illustrating some of the terms we use to talk about sea ice and sea ice structure. So here's the landfast ice that I showed you a bit ago that had the iceberg stuck into it. Because the landfast ice is basically attached to shore, you can get shear zones forming because the ice that's out in the open water or that's not attached to land, that makes flows, and those flows can move. And so at the boundary between the moving flows and the fast ice, you can get what are called shear zones. And sometimes you can see this where bits of ice can break off. If there's compression like you see there, you can see how that little gray bit, the ice is getting thicker there because the sea ice is actually pushing into and buckling the land fast ice. Where ice pushes together and stacks up, we form things called pressure ridges. And these can be quite difficult for sea ice travel if you're trying to go over the ice, because pressure ridges can be 10 or 15 meters high, and they're just big broken blocks of slabs. So a lot of the people that tried to travel on the sea ice in the winter, this was always one of the big hazards. It's hard to get over the sea ice. And of course, it's a great hiding place for things like polar bears. So you can't see them like you can out in the open if you're trying to catch them or if they're trying to catch you. So these areas are quite difficult. But these pressure ridges are also important because this is the kind of place you actually can form thick sea ice that then can survive the summer melt. And this is the kind of stuff that can turn into multi-year ice, which is important for summer sea ice cover. Depending on which way the wind blows, in this diagram it's showing that the wind is blowing, and so that's helping to push this ice into this multi-year ice flow, and that's forming the pressure ridge. And if the total Arctic basin's not frozen, so you have some open areas, then as the wind blows, it can open up what are called leads in tension. And those fractures then become places that whales can go and hang out in, so they can surface. Whales can go underwater sometimes for 20, 30, 40 minutes, maybe even an hour, but they're air breathing mammals. So they do have to come up and they have to be able to access the air to breathe. And so these leads can be quite important, especially for narwhals, beluga whales. They're small, they're very maneuverable. They can work their way through these leads. So this is some of the vocabulary in a relatively straightforward diagram that you might want to have as a record. I'll put this up. The video will be up, of course, but the PowerPoint's on Moodle as well, so you can come back and look at this. And then these diagrams are a little bit more detailed, but they show a lot of the same things. Small bits of ice is brash ice. These bigger things are icebergs. We'll talk more about them on Thursday. We give names to different sizes of ice flows, depending on how big the individual patties of ice are. Just like where we have pressure ridges, we have a hummock that sticks above the water, and we have a bummock that sticks below the water. Kind of interesting terms. And then down this next diagram down here kind of shows in 2 dimensions the frazzle ice, grease ice, pancake ice, eventually making a new flow, a lead in the flow, and then land fast ice. And if you read about Arctic exploration again, or you read about Inuit people traveling in the north, apparently you can walk on grease ice and it will support human weight, but it's thin enough that you can actually feel the waves underneath going through it. So like, I'm not going to volunteer to go walk on grease ice. Maybe if I had a dry suit, okay, maybe I'd try it. But you'll read some stories of like people going to the North Pole and like, they don't have a choice. Like the lead opens up, it's starting to open more. At night, it gets cold, grease ice forms. But the next day, if the lead continues, the people are stuck because they don't have a boat. So they just have to go for it. And like I'm not sure I'm brave enough to do that, but it will support human weight. Apparently, at least some of it will. Any questions about this stuff? So that last slide and this slide, this is a lot of the vocabulary for sea ice that you would need to know. And mostly it's descriptive based on the kinds of features that you may have seen in some of the pictures. Does anyone have questions about this? Where am I? 10:03. Okay. So now we'll just go through, and I don't need to belabor these too much. These are just some pictures illustrating some different types of sea ice. This is low tide, so you can see the land fast ice here. This fringe is almost melted for the summer, but again, this is 80 degrees north, so even though we're in August, it's still relatively cool. in the shade of the evening. But the ice here, you can see it's actually molded to the rocks. So this ice isn't floating out into the bay even during high tide because it's actually frozen and attached to the rock surface. So that's why it's called fast ice. This is a broader view. This is Eclipse Sound and looking into Baffin Bay. You can see a lot of land fast ice again here, but you can actually start to see some of these areas where you might have shear zones. We have this lighter blue ice that's land fast, but this darker blue ice then with some of these leads in it, those are actually ice flows. And just kind of for scale, these little parallel lines that go across the ice, those are from Comatux. And Comatux are the sleds that get pulled. Now they pull them a lot of times with snow machines, but they're also the sleds that can get pulled by dogs. And obviously this sled route's not open anymore. Well, I should say it is open, but it's not a trail that you want to go across because now there's a lead that's open up across that trail. What kind of ice is this? Should be pretty obvious.
Pancake?
Yeah, pancake ice. Very cool. I've never seen this in the Arctic, but I've actually seen this in some ponds forming on freshwater lakes. This is called silver dollar ice. And out west, they make things called silver dollar pancakes because they're just little small pancakes. So again, really distinctive texture. And then here, a couple of pictures that just show a whole bunch of different parts of the sequence of ice forming. So here's an open lead. You can see different generations of ice here getting progressively more opaque as they get older and thicker. This ice is actually old enough that it's got some snow cover. You can see here's a lead that opened up, but it's opening up slowly enough that it's still freezing at night. So it gets a really distinctive pattern. And then here's another open lead with new ice that's forming that's relatively clear, older ice that's been around long enough to have snow, and then this actually has an iceberg in it that you can see how much higher the iceberg is than the surrounding sea ice, which is relatively flat. Yeah. So sea ice is really important biologically. Birds can rest on it. Arctic foxes run across it and basically follow polar bears so they can feed on carcasses that polar bears have caught. Polar bears rest on it, and sleep on it, snooze on it, but also hunt from it. And even though seals and walruses could stay in the water most of the time, they like to come out on ice to rest and to give birth. Walruses also will use shorelines a lot. They'll have haul outs on shore, but seals tend not to do that. Seals tend to want to be out on the ice so they're feeling more protected. Okay, so relatively quickly, what's happening to sea ice today? Sea ice, this is a little GIF you can watch. We've already looked at this. The swing in the yearly sea ice cycle is getting bigger. So we still get a fair bit of sea ice in the winter again because there's no light and no solar heating, but it's breaking apart earlier in the summer and the extents are getting less and less in the summer. And it's not just that the extent or the aerial cover is getting less. Here's a couple of graphs that I'm not going to go through in detail, but if we look at this one in the lower left, another critical aspect that's not as obvious, sea ice is getting thinner. And that, as it gets thinner, it becomes less able to survive the summer. And so even though what we see visually is sea ice extent and it's going down, really a big part of the problem is that the sea ice that is there is getting thinner. And so if it thins too much, then it basically will all melt during the course of a summer. And there'll still be some sea ice, in the winter, but it'll be too thin to persist through the summer. Yeah, we've already talked about this a little bit. So now what I want to do is spend the last bit of class talking a little bit about how we monitor sea ice, because this is going to be important for you guys. And there's a number of sea ice services, like I said, nationally, they share some information. A lot of countries have their own, partly, because they can have it in their native language. Russian sea captains, would prefer to read the reports probably in Russian, etc. The U.S. Sea Ice Service does a whole Arctic sea ice map. And on their website, you can actually go into an archive and you can download this, guess what? As a shapefile. Yes. And it goes into GIS. So this is one of the cool things about this, the way sea ice data is made. You can, not everybody has to do this, but you can, and your groups can do this. You can download sea ice maps like this and take them right into QGIS or ArcGIS if you're working on that. And you can get weekly, monthly average sea ice extents that go right into GIS. And so you can actually download files. And for your groups, I do want you to do this as a group, and I'll help you do this with the downloads. Because what you'll be able to do for at least the last decade, you'll be able to do things like plot June sea ice extents over the last 10 years, and then see for yourself along your sea route what's happening to the sea ice on a given month. Right, so this is primary data that you can download and look at, so you can judge for yourselves along your route what's actually happening. A lot of the general sea ice maps, they tend to talk about sea ice surface concentrations. So when you're at 10% or on 10 on the concentrations, that's 10/10, so that's 100% sea ice cover. And you can see for this particular map, which is for February 19th of this year, so just a week or two ago. In these places on shore where you have land fast ice, you basically have 100% ice. So you could walk all the way across this and you probably wouldn't hit any leads. That's all relatively solid ice. But even in the main Arctic basin, you can see the coverage is only that 8 to 10, you can also read as 80 to 100% ice cover. And then as you get down into the North Atlantic, the colors go from orange to green, and that's going from like 60 to 80% ice extent to basically open ocean. Okay. And this is the other thing they look at. So they look at just percent of sea ice cover, but they also then try to sorry about that. They also try to classify the sea ice. So that's why we've been talking about this for a little bit. So you have first year ice, you have old ice. So now the old ice is really just in this relatively narrow belt, with some of it going down into the Canadian archipelago. But almost half of the sea ice for this February was first year ice. So that's pretty drastic. And so this is just showing you what some of these sea ice service maps look like. A lot of times you can break it down into smaller regions that'll have more detailed maps. So for example, the Canadian Sea Ice Service, which is fantastic. If we look at the Western Arctic, this is what you get as a map. So much more detailed. And this gets us to your assignment between now and Thursday. Because there's lots of information about sea ice, it's really hard to show it all on a map. And so one of the things that's been developed is something called the egg code. And that's literally what all these ovals are. These are eggs. And the egg code is a pretty cool device, because one little oval there tells you a bunch of stuff about the characteristics of the ice within this polygon. And it's pretty simple. The assignment I have is, you can do it in a group, you can do it on your own, but it's due before class on Thursday. It's only about a 1-page assignment. There's 1 page, it's got instructions and explanations, 1 page of questions, but it leads you through deciphering the egg code. And part of the reason that it's useful to decipher this is, one, when you go to the Sea Ice Services, you'll get maps like this. And so you don't necessarily just want to know, for example, this green here, if I go down to the color code, that's thick first year ice. But if I look at the egg code, then I also know that's 90% plus ice extent. And the ice, this tells me something about the thickness of ice and the form of the ice. And so in a lot of areas for this place, they're only reporting, basically the columns represent different batches of ice. So when we have 3 columns, these numbers apply to the thickest ice. These numbers apply to the thinnest ice as a description, and these numbers apply to the ice of medium thickness. And this will all make more sense as you go through the egg code. Yeah, I'm going to skip that for now. So this is sort of an explanation of the egg code. Like I said, this PowerPoint's online, so you can look at this as well. But this is also on the assignment. And what it shows you is that, in fact, this egg code is a relatively efficient way to give you lots and lots of information about the characteristics of the ice. So the upper numbers are total concentration. These numbers, you'll notice 5 + 1 + 2 add up to 8. So these are the partial concentrations. These numbers tell you about the stage of the ice. So is it new ice, first year, second year, whatever, and also something about the thickness of the ice. And then the bottom thing tells you for each of these concentrations what the form of the ice is. Pancake, small flow, medium flow, big flow. So this is a relatively efficient way to communicate a lot of different information once you understand how to decipher this. And you'll understand that by Thursday, because you're going to go through and do the short assignment. It shouldn't take you more than 15 or 20 minutes. And you'll feel like you learned something, I think, at the end. And what's also important is the shape files you download typically don't actually come with egg codes drawn on them. Sorry. But what they do have in the attribute table for the sea ice, when you bring the shapefile in, if you look at the attribute table, it actually has all of those things from the egg code in the attribute table. So you could make your own, you could shade your own map that's total concentration. You could shade your own map that is concentration of thickest flows, or what the form of the flows are. So all that information is contained there. So important for knowing how to interpret this data, to understand what the components of the egg code are. And yeah, and I think that's the last bit of here is just pictures from our trip in 2016. And the only thing I'm going to leave you with, so this is pretty stunning. This is what happens when the sea ice starts to melt. You get a layer of fresh water on top of the ice. And I'm in a sled here, a Commatuck, being pulled by a snowmobile. We're going back to Pond Inlet. And you look over the side and you kind of think, oh no, because you're just driving through water. And like, this is in the middle, like the water's probably 1,000 feet deep here. This is Eclipse Sound. And so, you know, and there are leads that are you know, like this is a freshwater lens on top of the sea ice, right? That's why the snowmobile is not just going super, super fast flying across the water, right? It's actually going through water. It's only about 10 or 12 centimeters deep, but like there's maybe a meter of ice between us and 1,000 feet of the ocean. And so it's kind of disconcerting, but like this is the ice, and it's this is how the sea ice breaks up. And melt lens on top, and then eventually that meltwater starts to drain down through the ice, and eventually that fractures the ice, and then it melts, and then you have open ocean. Okay, so that's enough for today. Hopefully you feel like you know a little bit about sea ice. The egg code assignment is up online. Like I said, it's only 2 pages, and the first half of the first page explains what the egg code is, and it just gives you 2 little practice assignments. So ask me if you have questions, but you should be able to work through that pretty quickly. And on Thursday, after our brief quiz, we will move on to talk about the second component of sea ice, which is icebergs. And we'll have some dramatic video to watch, which would be pretty cool. Okay? All right. So as always, email me if you've got questions about anything. Be talking in your group a little bit. Make sure you're making some progress towards having just a basic overview of your sea route. And I will see you all Thursday.
Thank you. Yeah.
Thank you.
Thank you.
Bye. Thanks, Ben.
Yeah. Have a good
I
day.
had-